Hi everybody, it's Data Bob here. I'm still in Florida. um, we're at where are we, Dad?
Seabreeze Recreational
The
Center
Seabreeze,
in the Villages.
Seabreeze Recreational Center in the Villages in Central Florida. I'm here visiting my dad. He's sitting here. He might help me with this. And this is going to be a quick and convenient introduction to computing streamlines with an Euler integrator or a numerical integration. The simplest numerical integrator is called the Euler integrator. And this video is for Callum Dicker, who asked for a review of this. And Callum, I'm sure, is studying hard. Callum, I know, is a very good student. I know that he's studying for this, and yeah. So this video is for him. And this is the most difficult video so far. So I'm going to try to get through this without making any errors. I might stop a few times just to look and try to think, because it's very easy to make a mistake with this computation. So just a little bit of review. We're computing streamlines. For this example, we're computing streamlines in 2D. What's a streamline? A streamline is a curve that's everywhere tangent to a vector field, right? In this example, the vector field is analytical. So this is the same example we went over in class. So that means, in this example, Vx is always minus y, and Vy is always x over 2. That means when it's an analytical vector field, given any position in the field, we compute the velocity. That's what the analytical vector field is. And that's as opposed to a sampled vector field in which we would need interpolation to get the vector samples. So we're just going to go over an example where we're given a streamline seeding point and we compute the next point on the streamline. That's what a numerical integrator is for. It's an approximation to the curve, the streamline curve. This is the simplest approximation to a streamline curve, and therefore it's the nicest place to start. This is the formula for the numerical integration. Actually, I have a little mistake there. Let me fix that. See, I already made a mistake, but I spotted it, so that makes it not count. So what does this mean? This means the next point on a streamline, that's what this symbol is, equals the current point plus the velocity at that point times a small unit of time we call dt. So that's how we interpolate that Euler integrator. So we're going to go through an example where we compute the next point on a streamline given a seed point and the velocity at that seed point. That's what the goal of this exercise is. And this could definitely be a test question, by the way. And we're going to choose a point that's very simple, so we don't need a calculator. I don't like having to use a calculator for an exam. So chances are you won't need a calculator for the exam. So in this example, we're going to choose a point x, a seed right here. Let me just double check. We're going to choose x equals 0 and y is minus 1. So the idea, this is x equals 0, y is minus 1, 0, minus 1, which is right here. So the question is, where is the next point along the streamline that's seated at that point, right? So Vx at this point is minus y. So it's Vx is minus y, so y is minus 1. So it's minus 1, which is 1. I didn't write that very clearly. Vy is x over 2. What is x? X is 0 over 2 equals 0. So Vx, Vy is 1, 0. So what is the formula then? The formula is SI. SI in this case is 0 minus 1 plus the velocity. The velocity is 1, 0 times dt. dt is given as a half. So to compute that, I'm going to simplify it. It's a vector, right? We're taking a point, a two-dimensional point, and adding a two-dimensional vector on there. So just to make it simpler and avoid mistakes, hopefully, I'm going to decouple the two vector components, the x and y components, and compute them separately, or compute the x coordinates separately. So that means we have S naught plus V1 times a half, right? So the x component is just 0 plus 1 times 1/2, which is 1/2. So 0 plus a half is 1/2. Right? So that's the x component of the next position. Then the y component is just s minus 1 plus v 0 times a half. What, right? So that is minus 1 plus 0 times a half, which is 0, equals minus 1. Hopefully that makes sense so far. So the next point on the streamline is 1/2 minus 1. 1/2 minus 1. Now where is that? That is a half unit over on the x direction and minus 1. So that's the approximate next point on the streamline. And it's not very exciting, but that's how you would compute it. And I hope that makes sense. Just for the fun of it, we can do another seed point. It's good exercise for me too. So the second seed point I was looking at was x2, y1. So x2 right here, 0. 2, 0. Right, so there's the second seed point. This is also very exciting, the second example. So we can, if we want, we can just draw a line. So in this case, x equals 2, y equals 0. So that means Vx equals minus y. So y is 0. So it's minus 0 or 0. And then Vy is, what is Vy? X over 2. 2 over 2 equals 1. So the velocity at that point points straight up. So we know just by looking at the velocity then that the next point should be somewhere above 2, 0. And the question is, where above 2, 0 is that? Right? So I'll do the same thing. Si plus 1 equals S. My writing is not that great. S2, 0 plus the velocity 0, 1 times the dt stays the same, 1/2. By the way, just a quick note about dt. This computation is usually calculated in software, not by hand. And the software that computes streamlines usually it assumes a very, very small value of dt, something much smaller than this, and often the user has direct control over the value of dt. So let's look at this. So we'll decompose the x and the y components again. So we have S2 plus the velocity times 1/2. That means 2 plus 0 times 1/2, which is 0. So 2 is the answer. The x component, or the x coordinate of the next point, is 2. And then we have, for the y component, we have S of 0 plus the velocity, which is, what do we say the velocity was? It is 1 times 1/2. Right, so the y component is equal to 0 plus 1 times 1/2, which is 1/2. So that's 1/2. So that means the next point on the streamline is Si plus 1 equals the two components, 2 and 1/2. Where is that? It's over 2 units and up 1/2 of a unit, so it's right there. So that's the first sort of edge on our streamline. Very exciting examples, but hopefully now it makes sense how to compute the points along a streamline. So that is a very quick and convenient introduction to numerical integration with an Euler integrator for the purposes of computing streamlines. For further reading, I'm going to reference again this amazing data visualization book, Principles in Practice, by Alex Telea. There's a good chapter on vector field visualization. I remember the first time I saw Alex present, he presented a very impressive flow visualization called 3D image-based flow visualization, which is a 3D flow visualization algorithm based on textures. That was at the IEEE Visualization Conference in 2003 in Seattle. I still remember that presentation. I still enjoyed that conference. It was very impressive. Yeah, some good memories from that year. If you have any questions, comments, suggestions, or if I made some error, please let me know. I think I got through that without making an error. Maybe. We'll see. I think I did, but yeah. Okay, thanks for watching. Okay, that one.